Okay, good afternoon, everyone. Am I audible to all of you? Now I'm audible. I think I'm audible to everyone. See, while sending messages in Zoom, just to select the option message to everyone. The message to everyone option you select and type the messages when I ask. Okay. So today's in the afternoon session, we are going to deal with some of the numericals. And I expect you to solve the numericals in a very rapid manner. And you have to share the answers with me in the chat box. Okay. By sending messages in the chat box. Is it all right? I'm not getting any messages in the chat box. Select the option send to everyone in the chat box. Okay, see this one. This is the abstract of what we have learned today morning. The first one is drift velocity equations. The second one is electric current. Then the potential relation between potential, resistance, and current. Then resistance, resistivity, unit of resistance and resistivity. Then current density. Then Ohm's law, failures of Ohm's law. Then where we apply the Ohm's law. Then equation for heat produced. All right. Then the Wheatstone's bridge principle. Okay. Then the EMF of the cells, that is a maximum potential difference across the terminals of a cell. Then the terminal potential difference and relation between the terminal potential difference and the EMF, V, the terminal potential difference, equals EMF minus product of I and R, where R is the internal resistance. And here we make a relation for the internal resistance, E by V minus 1 multiplied by R. Okay. Then cells in series combination and cells in parallel combination. And the laws, the last one, the Kirchhoff's rules, the junction rule, as well as the loop rule. So this is the abstract of what we have discussed in the morning. Now let's see this problem. Figure, both the switches S1 and S2 are closed. Both the switches S1 and S2 are closed. If both S1 and S2 are closed, there will be current flowing through S1 as well as S2. Okay. Then, see, the current here is I, and the current here it is I1 and I2. What about the brightness of this bulb as well as this one and this one? Brightness of the first bulb as well as brightness of second and third bulb. Do you think that all the bulbs will glow with the same brightness? I don't think so. What is your answer? Quick. I'll give you 20 seconds time. Brightness of all the three bulbs. What do you think? I'll give you 20 seconds of time. Either you can send messages in the chat box, or you can switch on the mic and speak. Okay, see, the total current here is I. It is being divided into I1 and I2, and we can write that total current I is equal to I1 plus I2. So the brightness in the first bulb, so the first one, brightness B1 will be greater than V2 or V3. V1 brightness in the first bulb will be greater than brightness in the second or third bulb. So that is the okay. Because it will turn black. Okay. So there is a technical advice. You have to send only messages. You don't switch on the mic. Some mic is on and that is creating disturbance. Please switch off the mic. Please switch off the mic and send only chats. That is SMS. In the next diagram, see this one. In the circuit given below, P is not equal to R. That P is not equal to R. And the reading of the galvanometer is same with the switch S open or closed. This is 2021 question. Okay. Then which of the option is correct? Reading of the galvanometer is same. Reading in the galvanometer is same with the switch S either open condition or closed condition. Then which of the options are correct? First option is IQ equals IR. IQ means current here, that is equal to IR. Need not be. Then second option is IR equals IG. IR equals IG. That means no current is flowing through this one. IR, that is a current through R. This is IR. This is IG. Current through IR equals current through IG. That means there is no current is flowing. No current is deviated through S. So that is correct option. Option B. Option B is correct. See the graph. A cell of EMF E and internal resistance small r is connected across an external resistance capital R. The graph showing the variation of potential difference across R versus this one. In the x-axis, resistance is taken. In the y-axis, EMF is taken. Okay. Variation of potential difference across R versus R. Okay. Potential difference versus R. Y-axis, potential difference is taken. X-axis, resistance is taken. Which of the graph is correct? I am not getting any chats. Here we can use this equation. V equals E minus IR or E equals V plus IR. So when we use this relation, V plus IR relation, we can find this one is a correct option. Now you see the circuit, two cells connected in opposition to each other. Two cells are there, they are connected. So this is the positive terminal and this is the positive terminal. Both the positive terminals are connected together. Both positive terminals are connected together. And as I told you in the morning, in such situations, EMF E will be equal to E1 minus E2. Okay. And if they are connected like this is E1, this is E2, this will be E1 plus E2 equals E. So in this case, EMF will be added up. And in such situations like this, EMF will be subtracted. So the current will be equal to 6 minus 4. This is 6 and this is 4 divided by total resistance. That is 0.2 ampere. Then potential difference across E1, the first one, is equal to V is equal to E minus IR. E minus IR, 6 minus I is 2, R is 2. So that becomes 5.6 volt. And in the second case, potential difference across E2, it is equal to, this is the opposite case, 4 plus 0.2 into 8. So that is 5.6 volt. Clear? Now see this question. A Wheatstone's bridge is given there with resistors 21 ohm, 35 ohm, 10 ohm, and R1. And what should be the values of R1 and R2 so that the bridge is balanced? Bridge is balanced. At the balanced condition, what should be the values of R1 and R2? See, here the condition is the bridge is balanced. If the bridge is balanced, the condition is P by Q. P by Q equals R by S. So in the balanced condition, there won't be any current through the galvanometer. So here the current is 0. So we can eliminate all these arrangements. We can avoid. We need not take all such arrangements inside that, since there is no current through that. Since there is no current, we can write 21 divided by R1 equals 35 divided by 10. So R1 equals 21 into 10 divided by 35. Okay, so you can solve it and you will get the answer. Here's another question. An electric heater is connected to the voltage source, voltage supply. An electric heater is connected to a voltage supply. After a few seconds, current gets its steady value. After a few seconds only, current gets its steady value. Then its initial current will be. There are 4 options given. First one is equal to its steady current. Second one is slightly higher than the steady current. The third one is slightly less than the steady current. Fourth one is 0. Which is the correct option? When an electric heater is switched on, it drags a lot of current initially, and once it is stabilized, it doesn't require that much amount of current. So the option is B, slightly higher than its steady current. Now let's see a few more questions. See the question number 2. A cell having an EMF E, and internal resistance R is connected across a variable external resistance capital R. As the resistance R is increased, external resistance R is increased, the plot of potential difference V across R is given by. Which is the correct option? A similar question, almost a similar question we have done just now. Okay. This one. It will be the correct option. Now, question number 3. If n cells, each of EMF E and internal resistance R, EMF E and internal resistance R are connected in parallel, n number of cells. Each of internal resistance each of EMF E and internal resistance R are connected in parallel, then the total EMF and internal resistance will be. This is a direct equation. Total EMF and internal resistance will be. What will be the value of total EMF and internal resistance? Connected in parallel. Okay. There itself we can say that EMF will remain the same. EMF will be E. The next one, the total internal resistance. Total internal resistance. If two resistors are connected in parallel, effective resistance will be R by 2. Okay, so if n number of such resistances are connected in parallel, obviously it will be R by n. So this is the correct option. Effective EMF will be E and effective internal resistance will be R by n. Clear? Okay, next question. Fourth question, question number 4. In a Wheatstone's bridge, if the battery and the galvanometer are interchanged, then the deflection in galvanometer will be. In a Wheatstone's bridge, if battery and galvanometer are interchanged, then the deflection in galvanometer will be. What will happen to the deflection in galvanometer if battery and galvanometer are interchanged? This is a tricky question. In a Wheatstone's bridge, at the balance condition, if we say that at the balance condition, if battery and galvanometer are interchanged, nothing will happen. No change will be there. No change will be there. Okay. But here it is not written. It is simply written as in a Wheatstone's bridge if the battery and galvanometer are interchanged. It's a tricky question. Okay, next one. The resistivity of alloy manganese is resistivity of alloy manganese. Question number 5. Resistivity of alloy manganese is first choice, nearly independent of temperature, increases rapidly with increase in temperature, decreases with increase in temperature, increases rapidly with a decrease in temperature. Which is the correct option? Just think and tell me. Question number 5. So we select manganese for making some of the resistance and all these things in our lab just because its resistivity is independent of temperature. As temperature goes up or goes down, that much impact will not be there in its resistivity, almost independent of temperature. So that is the reason why we select manganese in making lab equipment, lab devices and all these things. Now, next question. The current which is assumed to be flowing in a circuit, the current which is assumed to be flowing in a circuit from positive terminal to negative is called the current which is flowing from positive terminal to negative terminal. Which is that current? Direct current, pulsating current, conventional current, or alternating current? Which is the correct option? So it is the conventional current. Conventional direction of current is taken from positive to negative. Now, drift velocity of electrons is due to motion of conduction electrons due to random collisions, motion of conductor electrons due to electric field E, repulsion to the conduction electrons due to inner electrons of ions. Last one more was there. That collision of conduction electrons with each other. Okay, so which is the correct option? So the correct option is B, motion of conduction electrons due to electric field. Motion of conduction electrons due to electric field. That is the correct option. Now, in the absence of an electric field, the mean velocity of electric field is not there, electric field is absent, then the mean velocity of free electrons in a conductor at the absolute temperature T. Zero, independent of T, proportional to T square. Correct option. You're not putting any messages. I'm not seeing any messages here. Okay, question number 8. In the absence of electric field, the mean velocity of free electrons in a conductor at absolute temperature is, obviously it will be 0. Okay, next question. Let's see next question. A metal wire is subjected to constant potential difference. When the temperature of the metal wire increases, the drift velocity of electron in it. The metal wire is subjected to a constant potential difference. When the temperature of the metal wire increases, then the drift velocity of electron increases, decreases, thermal velocity of electrons increases, thermal velocity of electron decreases, and both decreases, which is the correct option in this. Question number 9. I'm not getting any chat or anything. See, the answer of this one, it is A. The answer of this one is A, increases, thermal velocity of electrons increases. Okay, so that is it. Problems? See this question. The electric circuit consists of 4 resistors, R1 12 ohm, R2 12 ohm, R3 3 ohm, R4 6 ohm, and are connected with a source of EMF E1 6 volt. E2 equals 12 volt. 2 EMFs are there, E1 and E2, and 4 resistors are there, R1, R2, R3, and R4. 12 ohm, 3 ohm, and 6 ohm. Okay, you're asked to find out determine the electric current flows in the circuit as shown in the figure. Determine the electric current flows in the circuit as shown in the figure. Electric current which is flowing here. You're asked to find out the value of electric current. Okay, first of all, this R1 and R2, they are connected in R1 and R2 are connected in parallel. So this R1 and R2, this will reduce to R1 parallel R2. This will be R1 R2 by R1 plus R2. This will reduce to, what are the values? R1 and R2, 12 and 12. It reduces to 6 ohm. Okay. Then EMF is okay. Now we have E1, E2, two EMFs. Then the parallel form of this R1 and R2, then R3 and R4. Three resistors and two cells we have now. Now we have to make, as per the Kirchhoff's rule, we have to make a loop. Kirchhoff's voltage loop we have to make, and based on the Kirchhoff's voltage loop, we have to make an equation. So what will be that equation? Only one current will be flowing through this loop because only one path is there for the current to flow. So minus I into R12 comes here. Now it is coming here as minus of the second EMF, that is E1. E1 because we are crossing the uh, electrolyte from positive to negative. Crossing the electrolyte from positive to negative. So it is negative, minus I R3 minus I R4. Okay. Then one more EMF is there. This is E2. E2 we are crossing the electrolyte from negative to positive. So this will be plus. Plus E2 equals 0. Plus E2 equals 0. So this is the equation. From this equation, you can solve out the value of I, current I. When you solve it, R12, the value of R12 is 6. So minus I multiplied by 6 minus E1. E1 is 6 volt minus I multiplied by R3. R3 is 3 ohm minus I multiplied by R4. R4 is 6 ohm plus E2. E2 is 12 volt. 12 equals 0. Here you get I is equal to how much? I equals, you will get the value of I equals 2 by 5 ampere. See how it is solved? Okay, let us move on to the next one. Determine the electric current that flows in the circuit as shown in the figure. Electric current that flows in the circuit as shown in the figure. Here again, parallel combination is there. This is 20 ohm. Can you see it? This is 20 ohm and this is 5 ohm. This is 10 ohm and this is 6 ohm. Okay, 12 volt and 8 volt. Okay, so first one is we have to take a loop. So this one is parallel, 20 and 5 parallel. what effective resistance we will get when we calculate 20 and 5 parallel? That is, R is equal to 20 into 5 divided by 25. That is equal to 100 by 25. It is equal to 4 ohm. See the voltage here, it is positive, negative. Here again it is positive, negative. So the net EMF will be equal to E1 minus E2. That is 12 minus 8. That is 4 volt. Total resistance is equal to 10 plus 6 plus 4. That is equal to 20 ohm. Then the current I will be equal to 4 by 20. 0.2 ampere. Okay. See this one, very simple one. Let's see the next one. Question number 12. Question number 12, let us see. Calculate the current that flows in the 1 ohm resistor in the following circuit. Calculate the current that flows in the 1 ohm resistor, that is this resistor. That we have to find out. Okay. So that we have to take the loop EFCBA. First, let us take the loop EFCBE. That loop, this loop we have to take EFCBE. What are the potentials there? First one is I2. 1 ohm here and I2. So 1 I2 minus, sorry, plus 3 I1. It is coming to negative and going to positive, coming to negative and going to positive. Okay. So that will be my minus. Okay. So here we will change. 1 second. This is minus I, minus 1 into I2, minus 3 into I1, plus 9 minus this one. Two into I1 equals 0. This equation we can make it as this equation we plus 3 I1 plus 2 I1 equals 9. That is 5 I1 plus I2. Very simple. 5 I1 plus I2 equals 9. Now the second one. EADFE. EADFE. So first one is that this one 3 into I1 minus I2. Three into I1 minus I2, that is this one 3 ohm here, and I1 minus I2 is the current which is flowing. And now here 1 into I2 minus 1 into I2 equals 6. That is 3I1 minus 3I2 minus I2 equals 6. I1 minus 4I2 is equal to 6. Like that we can write. Then we can solve for I1 and I2. Two equations are there. This is equation 1 we get. This is equation 2 we get. We can solve equation 1 and 2. We can solve equation 1 and 2 for variables I1 as well as I2. Two equations are there and we got two variables also. So we get I1 equals 1.83 and I2 equals 0.6, 0.13 ampere. Like that we get. Okay, let's move on to the next one. Find the equivalent resistance using Kirchhoff's laws. Equivalent resistance of these things using Kirchhoff's laws. Okay, so let us see. We can start. So this is I, current I. This is I plus I2. This is total current is 3. This is 3. So the current through this one will be 3 minus I, because I ampere will be flowing through one arm and the remaining 3 minus I ampere will be flowing through a remaining arm. And here which is going up, this is I2 and this is 3 minus I plus I2. So this I is coming here, I2 is coming here, then I plus I2 will be. Okay, so these are the divisions in current. And so let us take the first one. The first one like this, 6I plus 3 into I plus I2. 6I is this one, 6 multiplied by I plus 3 into I plus I2 there. Okay, so that will be equal to the EMF. That will be equal to the EMF E. This will be connected to a cell, no? This will be connected to a cell. So potential across this one plus potential across this one, that will be equal to the EMF E. So that is the first statement. Then the second statement is, see this one, the lower one, 3 into 3 minus I plus 6 into this one. The current through that 6 ohm, current through that 6 ohm is 3 minus I plus I2. 3 minus I plus I2. 3 minus I plus I2 or 3 minus I Okay, so this again will be equal to E. Because it is connected to a cell, it will be equal to E. So two statements we made. From these two statements, we will get. We can solve these two equations. By solving the first equation, we get 3i, 6i here, 3i here. So it will be 9i plus 3i2 will be equal to E. First equation. From the first equation, 9i plus 3i2 equals E. Then from the second equation, after solving the second equation, we get 27 minus 9i minus 6i2. 27 minus 9i minus 6i2 equals okay. So we got two equations. This is equation 1 and this is equation 2. Very slowly I am going. I want to convince you how we are getting these kind of equations and how we can solve these questions related to Kirchhoff's laws. Then when we apply KVL in loop 1, apply KVL, Kirchhoff's voltage law in loop 1, we get 6i minus 3 into 3 minus I, that is 6i minus 3 into 3 minus I. How much will be? What will be the value? This will be 0. Then from this we can get 2i equals 3 minus I equals value of I equals 1 ampere. So we get I equals capital I equals 1 ampere. Then substituting the value of I there, we will get substituting the value of I here. In this equation, we get the value of I2 as how much we get the value of I2? We get 9. Sorry, no, 9. No, not 9. We won't get 9. If we get I1 equals 1 ampere and I2 equals 1 ampere, then the value of E will be equal to, what will be the value of E? We get the value of E as 12 volt. Then R. 12 by 3 equals 4 ohm. Now next thing we require, Yeah, that much is only, that much is, that is the end of this problem. Okay, see once again. Okay, let's move on to the next one. The plot of variation of potential difference across a combination of three identical cells in series versus current is shown in the figure. Variation of potential difference across a combination of three identical cells which are kept in series versus current is as shown in the figure. What is the EMF of each cell? As I told you in the morning, this point represents the EMF. So this is the total EMF of all the three cells when current reduces to 0. Here the current is 0. See here at this point the current is 0. Okay, at this point current is 0. So the potential difference there is 6 volt. So this is open terminal potential difference. Open terminal potential difference is called, this is open terminal potential difference. 6 volt is the EMF of three identical cells. Okay, so we need the EMF of each cell. So EMF of each cell will be equal to E equals total EMF, that is 6 volt divided by 3, that will be equal to 2 volt. Simple. When there is no current drawn from the cell, EMF developed there is called the, sorry, voltage developed there is called the EMF. So there is no current drawn from the cell. Here the current is 0. So the potential difference there is 6 volt. So this 6 volt itself is its EMF. Okay, so the total EMF is 6 volt. EMF of each cell is 2 volt there. Next one. A 15 volt battery of negligible internal resistance is connected across a 200 volt battery and a resistance of 39 ohm as shown in the figure. Okay, find the value of the current. So 5 volt battery is there, 39 ohm resistor is there, and another 200 volt battery is there. Okay, here again the problem is that these batteries are connected. See the 200 volt, 200 volt positive is here. Okay, and 5 volt positive is here. So the positive and positive are connected in a similar way. So the net voltage will be 200 minus 5. Okay, so net voltage. So we need to find out, what we have to find out, find the value of current. So find the value of current. So current is equal to V by R only. So here V is 200 minus 5 divided by R is 39. So that is 195 divided by 39. So that will be 5. 5 ampere. 195 by 39, that will be 5 ampere is the current. Clear? So very simple thing. Okay, let's move on to the next one. So remember one thing, if two cells are connected like this, the effective EMF will always be E1 minus E2. And if two cells are connected like this, negative to positive and like this is E1, this is E2. Here the EMF will be E1 plus E2. This always you have to remember. Now see this question. A battery of EMF 10 volt and internal resistance 3 ohm is connected to a resistor. If the current in the circuit is 0.5 ampere, find the resistance of the resistor and the terminal voltage of the battery. Try this. First one is the resistance of the resistor. So current I is equal to V by R plus R, V by R plus R. V is given there as 10, small r and capital R. Internal resistance is 3 ohm. So small r is equal to 3 ohm connected to a resistor. And the current in the circuit, so I equals how much is 0.5. Okay. Now V is given as V equals 10 volt. So this is 10 by 3 plus capital R equals 0.5 ampere. Then 3 plus R no need to write. $17 ohm. That is the resistance of the resistor. Now the terminal voltage of the battery we need to find out. Terminal voltage of the battery. How to find out the terminal voltage of the battery? Terminal voltage is the second one. Terminal voltage V equals I into R. I is equal to 0.5 into R is 17 ohm. So it will be 8.5. Okay. See this one. $8.5. Okay. So we move on to the next one. A battery of EMF 6 volt and internal resistance of 2 ohm is connected to a resistor. If the current in the resistor is 0.25 ampere, find the resistance of the resistors, terminal voltage of the battery. Question number 17. See this one. Can you tell the answer? So let us see I, current I. First one, current I is equal to E by R plus R. EMF 6 volt. 6 volt divided by capital R is capital R plus small r is 2. The current there is 0.25. Okay. And we get the value of capital R as how to find out that? 6 by 0.25 equals R plus 2. 24 equals R plus 2. Therefore, R equals 22 ohms. Now the second one, second question. Terminal voltage of the battery, that is V equals I into R. I is given there as 0.25. R is given there as 22. 0.25 into 22. That will be 5.5. 5.5 volt. Okay. Just take down this. Okay, the next one. Network of PQRS. Network of PQRS has batteries of 4 volt and 5 volt and negligible internal resistance. Internal resistance there is negligible. A milliammeter of 20 ohm resistance connected between P and R, between the points P and R. Calculate the reading in the milliammeter. What is the reading in the milliammeter that we have to find out? Here again, we have to go for the loop rule. Okay, so what are QRS? So three loops we can take: PQRP, PRSP, PQRS, like that. Three different loops we can take. And in the first loop, PQRP, when we consider loop PQRP, PQRP. So we are going from positive to negative through the electrolyte. So it will be -4. Okay, then 60 ohm resistor is there, 60 ohm resistance is there. That 60 ohm resistance, we can take it as. Okay, so we have to mark the current also, no? Okay, we have to mark the current also. So this this will be I minus I1. Okay, so -4 will be equal to this loop PQRP. 4 volt will be equal to -4 volt will be equal to 60 into I minus I1 minus 20 I1. So when we open this, we will get 60I minus 60 I1 minus 20 I1 equals -4. Okay. So when we divide it with 4, we'll divide everything with 4. So 60 I1 and 20 I1, we get 80 I1. So 60 I minus 80 I1. This will be -4. We will divide it with 4. Dividing it with -4. Then we get 20 I1 minus 59 equals 1. Now the loop P. Now the second loop is PRSP. Second loop PRSP. PRSP. P here, RS here, P here. Okay, what we will get? The voltage there is 5, so -5. This one. -5 plus 200I plus 20 I1 equals 0. We can write. Okay. Then we can rearrange. We can divide it with 5. This 200I plus 20 I1 equals 5. Then we will get 40I plus 4 I1 equals 1. Then let us consider this as equation 1 and this as equation 2. By solving equation 1 and 2 from 1 and 2, from equation 1 and 2, we will get the values of I1 and I2. I1 will be equal to 11 by 172 ampere. Okay, just see that. Clear? Okay, let us move on to the next question. Yeah, this is same thing only. Now, question number 19. This is a typical question every time we get. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1 into 10 power minus 7 meters square, carrying a current of 1.5 ampere. Assume the density of conduction electrons to be 9 into 10 power 28 per meter cube. Okay, so that 2014, they asked the same question. All right. Now, how to solve this question? So it is something related to drift velocity and all. So we have a direct equation for drift velocity. So that equation is I equals N A Vd into E, direct equation. And in that we need current. Current is there, 1.5 ampere. Okay. Density of conduction electrons, that is 9 into 10 power 28 meter cube, is there. Area is there, 1 into 10 power minus 7. So we can write 1 by 1 there. We have to find out the average drift speed of conduction electrons in copper wire of cross-sectional area this much. So A here is 1 into 10 power minus 7. We have to find out Vd. That's all. So Vd equals I by N A E. So N is there, A is there. Now E is required. Na? E is equal to 1.6 into 10 power minus 19 coulomb. Substitute the values of I, N, A, and E. You will get the answer. So we will get the answer as 10.4 into 10 power, how much it will be? 10 power, it will be minus 4, 10 power minus 4 meter per second. This is a typical question. Most of the time it appears in the board exam. Okay, we'll move on to the next question. Using Kirchhoff's rule, determine the potential difference between the points A and D when no current flows in the arm BE. See, there is no current from B to E. There is no current through this one. I here is 0. No current is flowing between B and E. Okay. So we have to find out potential difference between the points A and D. That is this point and the point D. Potential difference between the points A and D we have to find out. Let's see how we can find out the potential difference between the points A and D. So VAD, potential difference between the points A and D, it is equal to how many batteries are there? One is there, and two batteries. Two batteries are there. So one is 6 volt and the other one is yeah. 6 volt plus 3 volt plus IR1. Since there is no current here, I is equal to 0. There is no current here. See, we are coming like this, 6, like this. This is 6 volt, this is 3 volt, the IR1, but this I is 0. So VAD equals 6 plus 3, that is 9 volt. Okay. Next one. Calculate the current drawn from the battery by the network of resistors shown in the figure. There's a network of resistors. After seeing the diagram, do you get any idea? Just see the diagram and try to recollect any idea. This is just like, so this is a typical figure. Most of the time it appears in the examination. There will be 5 resistors, 1, 2, 3, 4, 5 resistors will be there like this. 3 resistors in a row, and in between the 2 resistors, so this is the pattern. Okay. So we stretch this to this end and this stretch this to this end. So that it will be in this shape. 1 ohm, 2 ohm, okay. So this is 2 and 4. This is 1 and 2. This is an equivalent diagram. So this is the 5 ohm. So it is just like a Wheatstone's bridge. So P by Q, that is 2 by 4, it is equal to 1 by 2. So P by Q equals R by S. So bridge is balanced. So we can remove this resistance. Okay, that resistance can be removed. So when we remove this reduces to 2 plus 4, 6 ohm. And another 1 plus 2, 3 ohm. 6 and 3 parallel. So when it is 6 and 3 parallel, it becomes 6 into 3 divided by 9. 18 by 9 equals 2. In connection with this, there is another problem here. We have 3 resistors and we connect the resistance like this. Previously it was there. Since the parallel and series combination they have eliminated from the syllabus, now these kind of problems do not appear. So R1, R2, R3, 3 resistors are connected like this. What will be the effective resistance of this combination? So this is another typical question, which is just like the question what we have discussed just now. So see this, let us take R1 only initially, R1 only, this is R1. So this is point A, point B, point C, point D. R1 is between point A and B, point A and B. Listen carefully. So R1 is between point A and B. Now what is R2? R2 is between one end is B, next end is C. See, one end is B, next end is connected to C. C is in turn connected. So in effect, R2 is also connected between A and B. Okay. So this is R2. One end of R2 is B itself. The other end of R2 is C. C is in turn connected to A. C is in turn connected to A. Now R3 remains. One end of R3 is D. One end of R3 is D. D is in turn connected to B. So this is D. D is in turn connected to B. And the other end of R3 is C. C is in turn connected to A. Other end of R3 is C. C is in turn connected to A. This is the equivalent diagram of this particular type of combination. And when we combine three resistors like this, what we get? See here, what we get? R1, R2, and R3. All the three resistors in parallel. All the three resistors are connected in parallel. So if this kind of question arises, it can appear in the case of resistor as well as capacitors also. See this one. If connections are there like this, three resistors, 1, 2, 3, or three capacitors, 1, 2, 3, and they are connected like this. In the middle, one resistor or capacitor is there. So altogether 5 elements are there connected like this. Then it reduces to Wheatstone's bridge. And if resistor is not here at this point, if resistor is not there, then it becomes a parallel combination. All resistors are connected in parallel. All right. Now question number 22. See the question number 22. Two cells, EMF 1.5 volt and 2 volt, having internal resistance 0.2 ohm and 0.3 ohm respectively, are connected in parallel. Calculate the EMF and internal resistance of the equivalent cell. Two cells are there. One is EMF 1.5 volt, and the second one is having an EMF of 2 volt, having internal resistance 0.2 ohm and 0.3 ohm respectively, and they are connected in parallel. Calculate the EMF and internal resistance of the equivalent cell. Okay, so how to solve this? Just to see how to solve this. See here, two cells are there, and the two cells are connected in parallel. We need the EMF and internal resistance of the equivalent cell. There is a direct relation for that. EMF will be equal to E1 R2 plus E2 R1 by R1 plus R2. You can solve this. E1 is 1.5 volt, R2 0.3 plus E2 2 volt multiplied by 0.2 divided by 0.2 plus 0.3 is 0.5. When you solve it things together, you'll get a value of 1.7. This is the equivalent EMF. Okay, so the first one is equivalent EMF. Second case, what is that? Internal resistance. Internal resistance. Two cells are connected in parallel. So the will be equal to R1 R2 by R1 plus R2. 0.2 multiplied by 0.3 by 0.5. So that is the internal resistance. You get 0.12. See this. Okay. Now the next question. Figure shows a plot of terminal voltage V versus the current I of a given cell. Plot of terminal voltage V versus the current I of a given cell. Calculate from the graph EMF of the cell and internal resistance of the cell. So now it is just become very easy. You know what is EMF and what is the internal resistance. You can easily calculate. So you remember the relation V is equal to E minus IR. Using that, E equals V plus IR. You can write, and using that relation, you can easily calculate that. Now, how much will be the value? So EMF, it will be 6 volt. EMF will be 6 volt. 6 is equal to, the question is, sorry, here the voltage is 6 volt. Sorry. At this level, we can take this level. So 6 equals V is 4 volt. 4 plus I is 1 ampere. 1 into R. So 6 minus 4 equals R. So R is equal to 2 ohms. Okay. Now, question number 24, using Kirchhoff's rules, determine the value of unknown resistance R so that no current flows through 4 ohm resistor. So there is no current flowing through this section. This section, there is no current. Also find the potential difference between A and D. Let's try this. Now let us take the loop AB. ABEFA. ABEFA. So minus 9 plus 6. This is 9. This is 6. 1 ohm and 1 ohm. That 4 ohm, there is no current now. So 4 into 0. 4 into 0. plus that two resistors are there, 1 ohm and 1 ohm, that we have to accommodate. So the current through that one is I. So 1 into I plus 1 into I. Okay, so this is minus 9 plus 6, it is minus 3. This reduces to 0. This is 2I. That is, this equation reduces to 2I minus 3 equals 0. 2I minus 3 equals 0. Now BCDEB. This loop BCDEB. 3. This is minus to plus. It is entering from negative to positive directly. So plus 3 plus this loop BCDEB. 4 into 0 minus 6. So this will reduce to IR equals 3. From this equation, we will get 1.5 ampere. So here 1.5 into R equals 3 and R is equal to 2. R is equal to 2 ohm. Now we need the potential difference between A and D. Potential difference between A and D. So that is VAD. VAD. A and D, potential difference between A and D. So there in between these two, we have 9 volt, we have 3 volt, and there is a potential drop across the resistor R. Well, three things are there: 9 volt, 3 volt, and potential drop across the resistor R. And we get this 9 volt is here positive, then 3 volt is negative. 9 minus 3 plus IR. Sorry, minus IR. 9. This is minus IR. Okay, so 9 minus 3 minus IR. So that will be equal to 9 minus 3 minus value of I is 1.5 and value of R is 2. Okay, so that is 9 minus 6. It is equal to 3 volt. 9 minus 6, it is equal to 3 volt. So that is the potential drop across the points A and D. Hope you understand the topic current electricity. We will meet again in the evening 6:30 p.m. With the topic magnetic effects of current. Thank you.